So today we are going to discuss about lecture number 39, phasor diagram. The subtopic for this synchronous motor with different excitation. You are very familiar about the synchronous motor principle. So in synchronous motor principle, what happened? There are two windings are there. One is armature winding, another one is field winding. Armature winding will be in stator part, field winding will be in rotor. So in armature only you are going to give AC supply, three-phase AC supply. Field winding we are giving DC excitation. Okay. So the main operation of this particular topic, synchronous motor with a different excitation, we are giving anyway, we are going to give DC excitation to the field winding. Okay. Now if you change this DC excitation, okay, if you change this DC excitation, what happens to the phasor diagram of synchronous motor? That is, phasor diagram means which having the parameters called IA, that is armature current, impedance value, reactance value, voltage value, everything, all the parameters which will be incorporated, that is known as phasor diagram. Okay. Now if you change this DC excitation step by step, if you change DC excitation step by step, there will be a changes taken place in the parameters which is available inside the machine. Changes in parameters. Okay, changes in parameters. So there are different three types of excitations are there. There are three types of excitations are there. One is a normal excitation. Okay. There are three types of excitations are available, namely the first one will be normal excitation. The meaning of excitation means supply, input. Okay, input. Normal excitation. In normal excitation, the back EMF, that is EB, which is equal to terminal voltage V. Okay, back EMF EB, which is equal to terminal voltage V. That is known as normal excitation. The second one will be under excitation. Under excitation. So in under excitation, the back EMF EB is lesser than the voltage. Okay, lesser than the voltage. Third one will be over excitation. Over excitation. The meaning of over excitation, the back EMF EB is greater than V, is greater than V. Okay, greater than V. Okay, there is a relationship with the power factor by using this normal excitation, under excitation, over excitation. In normal excitation, in normal excitation, the current value, okay, the current value will be, it is not leading or lagging, okay, no lagging or leading, it is a unity, okay, which is unity. And in under excitation, the current will be lagging current, lagging current. In over excitation, it will be leading current, which is leading current, which is leading current. So if the current will be here, it will be unity, means the power factor is also be unity. The power factor is unity power factor in normal excitation. In terms of lagging, the power factor will be, the power factor will be lagging power factor. The power factor is lagging. In leading current, the power factor will be leading. The power factor is leading. So you know the basic difference between lagging, leading and unity. Okay, lagging, unity means which is applicable for resistance. Lagging means which is applicable for inductance. Leading means which is applicable for capacitors. Okay, you all know the lagging, unity means which is applicable to resistance. Lagging means which is applicable to inductance. Leading means which is applicable to capacitors. Okay, which is applicable to capacitors. This is a basic. Okay. Now by using this concept, normal, under, over excitation and lagging power factor, unity power factor, now I am going to draw the vector diagram. Okay, vector diagram. Vector diagram is other name called as a phasor diagram. Vector diagram. Okay, the first one. First diagram will be when EB equal to V. Okay, when EB equal to V. Now how to draw this diagram? Now I am drawing X and Y axis. Okay, this is X, this one is Y. Okay, now I am plotting 0. Now I am plotting 0. First we have to, from 0 we have to draw the voltage. Okay, this is the voltage. I understand? This is my EB equal to V. Okay, EB equal to V. And during this time we are getting the armature current will be lagging, because this is the basic idea, lagging in synchronous motor. Okay, just lagging it, and the angle will be phi. It is lagging. Here when EB equal to V, which is lagging power factor, the power factor will be lagging it, because based upon the current type, it is lagging power factor. Now the back EMF, this is EB. Okay, now your the resultant voltage, this is ER. This is ER. Now join these two. Okay, so the angle between this ER and V, the angle between ER and V, the angle between ER and V will be, this one will be alpha. The angle between the EB and the V, this is B, okay, EB minus B. This one is also the alpha. The angle between ER to IA will be theta. It will be a theta. Okay, this is my figure 1. Okay, this is one of the 10-mark question in your examinations. This is figure 1. Okay, figure 1 for when EP equal to V. Okay, EP equal to V means it will be a normal excitation. Okay, this is normal excitation. Normal excitation. Okay, now we are going to draw the second diagram. Second diagram will be EB is less than V. When EB is less than V, it will be under excitation. Under excitation. In under excitation, which is lagging power factor. I have to draw different. Lagging power factor. This is figure 2. Okay, figure 2. Okay, now same method. First, draw x and y axis. Okay, x and y axis and mark 0. Okay, mark 0. Now step 2, you have to draw a voltage, and here it will be a lagging power factor. So the armature current IA, which is lagging, the angle between IA to V, which is phi, which is now what happened? Okay, so when EB is less than V, so during this time the EB value will be there, right? Okay, the EB value, you will start move towards your V value, okay, towards your resultant. So this EB will be somewhat a little bit of increasing, okay, a little bit of increasing it, and this is, and now you have to draw a resultant because there is no disturbances in ER. Okay, there is no disturbances in ER. This is ER. Then join this line. Okay, then join this line. The notation, this one will be ER. This notation will be EB. The angle, which is alpha, this is alpha, and the angle between this ER to IA will be theta. Okay, will be theta. Now Bec- By seeing this, both figure 1 and figure 2, what you are understanding? When EB equal to V, that is when voltage V equal to 230 means EB should also be 230 volt. Okay, should also be 230 volt. Okay, but when it comes to EB is less than V, the EB value will be 210. Okay, here I will mention EB equal to example 200 volt. V is also 200 volt. But in under excitation, the EB equal to 180 volt, but V equal to 200 volt. Okay, that's what we are getting, this lesser voltage. Okay, which will be lesser voltage. Understand or not? This is for figure 1 and figure 2, like normal excitation and under excitation. Now the third diagram, okay, third condition will be, the third condition will be EB is greater than V. Okay, EB is greater than V, which is over excitation. Which is over excitation. So during this time in over excitation, which is leading power factor. Okay, which is leading power factor. So mark down, this is figure 3. Figure 3. In over excitation, first step, again you have to draw x and y axis. Mark down, this is 0. Okay, then we have to draw the voltage. Okay, this is voltage. Since it is a leading power factor, okay, it is a leading power factor, the current value will be leading it, right? This is leading IA. Okay, the angle between this V to IA will be phi, which is phi, which is phi. Now you have to draw the EB value. Okay, so here the EB value will be very high. Okay, which is very higher value. Okay, which is very high. The angle between which is alpha. Okay, now join. See, all the lines should be horizontal. Okay, the line should be horizontal. So here there is no disturbances in ER. The ER value will be, sorry, the ER will be, it will be leading. Okay, which is leading it this way, this way. Okay, which is leading it. Now from ER you have to join. Okay, you have to join it because the ER will be coming between the negative quadrant, that is in second quadrant. This is my second quadrant. Second quadrant. This is first quadrant. Okay, the ER will be comes towards EB. Okay, which towards EB. Understood, Arna? Understood. See, the angle between this V to ER will also be alpha. The angle between this ER to IA will be theta. Okay, I am not disturbing any type of angle. Okay, so when EB equal to B in over excitation, the EB value will be how much? EB value, for example, these are examples. Okay, EB value will be 300 volt, but V value will be, it will be 200 volt, but it is moving it, okay, which is move towards this back EMF, okay, which is to move towards back EMF. Okay, are you understand? This is nothing but leading power factor. Now the figure 4 which is for unity power factor. Okay, so unity power factor. So in synchronous motor, normally the unity power factor will be taken place in resistance parameters. But in synchronous motors, we are having the two windings, one in armature, another one is field. So in both the windings, the resistance are available. Due to this resistance parameters which is available in the synchronous motor machine system, so the condition will be here the EB is greater than V. Okay, so when EB in over excitation system also the unity power factor will be taken place, which will be in taken place. Okay, please take down which will be taken place. Now you have to draw the phasor diagram, that is vector diagram. Okay. 0, this is V, this is V, this is 0, V. Understand? So unity power factor, what happened when unity power factor, the current value, okay, IA value will be equal to V. Please take down, IA value will be equal to V. Okay, so IA will be available in the same line. This is IA, okay, which is available in the same line of V. Okay, so in unity power factor, phi value should be 0. Okay, unity power factor. How to get the unity power factor? Cos phi, that is cos 0 equal to 1. Okay, when it will be phi value should be 0. Okay, then only the cos 0 should be 1. Understood or not? So then the EB value, because EB will be very much greater than V. Okay, the EB value which will be flow towards, this is EB, and again you draw. Once you draw the EB, then you draw the horizontal line, then draw this ER. Sorry, again mistake is wrong. The ER value will be slightly, because the ER value will be come here, which will be flowing towards. Okay, EB will be flow towards ER, but ER will be flow move towards EB. Okay, anyway it should be comes in second quadrant. Okay, second quadrant. Then join ER and V. The angle between this V to ER will be alpha. This one will also be alpha. The angle between ER to IA will be theta. Okay, which is theta. Any doubts? Any doubts? Now the formulas. Formula, please take down. First two. For lagging power factor, the EB formula, EB equal to square root of V minus IA ZS cos of theta minus phi whole square IA zs sine of theta minus phi whole square. Sorry. Whole square. The load angle formula alpha equal to tan inverse of Ia sectors sine of theta minus phi divided by V minus Ia sectors theta minus. Okay. So this is the formula for lagging. Okay. In terms of leading perfect. In terms of leading perfector, EP equal to V plus Ia Zs cos of 180 degree minus theta plus phi plus j into, because we are writing in terms of imaginary terms, Ia Zs sine of 180 minus theta plus phi. Okay, plus phi. Alpha equal to tan inverse of Ia Zs sine 180 minus theta plus phi whole divided by V plus Ia Zs cos of 180 minus theta plus phi. Theta plus phi. This is for leading perfect. And the third one, unity perfect. Okay. Third one will be unity perfector. Unity perfector EP equal to V minus Ia Ra J into Ia into Xs. Alpha equal to Ia Xs. P minus Ra. Okay. So this is the phasor diagram as well as in terms of normal excitation of our synchronous motor. Okay, of our synchronous machine. Okay. So from the phasor diagram, you can know the basic equations. Basic equation: impedance Zs is equal to Ra plus Jxs, theta equal to tan inverse of Xs by Ra. Okay. Zs, magnitude of Zs is equal to square root of Ra square plus Xs. The unit is ohms. This is basic equation. Basic equation. Okay. Any doubts, students?